Thank you very much for great talk. It's extremely long, so maybe let's everybody.
I'm surprised I'm still talking, not guessing.
Thank you very much.
Okay,
I was waiting for that. So nice. Cheers. Right, questions.
Questions, comments. So I think Kate, so please just unmute and talk.
Okay. My question is, in your model of the photon, do photons scatter off each other?
No.
If not, why not?
Well, if not, why not? Well, because each one's in its own space, really. Because they're emitted, and they can do, but it's actually very difficult. Now, there are two ways they can scatter off one another. One of them is the box diagram of QED, because remember, this theory doesn't contradict QED, it just underpins it. So that's where you have electron-positron pair running around a box. So they can scatter off each other with that diagram, and that's been observed. However, the other way that photons, the only way that photons can interfere, have you heard of fat photons, PHAT photons?
No.
So these are photons that come in at energies of 1, 4, 9, 16, etc. And what these are superimposed photons. So they're not really scattering off one another, but they're sitting in the same space-time unit as one another. So if you take two fields, because the energy density field goes as the field squared, if you take two photons and stick them right on top of one another, not as in a laser, but as in a fat photon, then the total energy is going to be multiplied by, because you have two photons, a factor of 4, if you have 3, a factor of 9, and so forth. So these are a thing, and it's not widely known, and it's not widely advertised, but I think this is a very important field of study going forward. So the photons don't scatter from each other because if you have an emitter and absorber, they're really at the same place in space-time. There's no room for anything else. There is nothing else in between. So that's why they don't scatter. And also, the equations are linear, so for the photon, they're linear.
So if I have two laser beams and I direct them toward each other, the photons going through that are not going to encounter each other. Is that what you're saying?
Well, actually, maybe there is a way of doing it. What you do is you take a big laser and you direct them against one another and you create twisted modes. In other words, you arrange the right circularly polarized on right circularly polarized, the two things come in. What that'll do is that'll give you stopped light. Now that is not a photon, that's a state of matter. And then if you take a perpendicular laser beam and try and hit it, you then scatter off that, but you wouldn't be scattering off light, you'd be scattering off matter. So I suppose the answer to your question is yes or no, yes and no then.
So you can make stopped light that has energy less than an electron?
I think so, yes. Yeah, people do this because people stabilize laser cavities by using the twisted mode. So it's become an engineering thing. So in that kind of, in other words, in a laser cavity, there will be some element of material stuff there. And I would then expect to see scattering of a perpendicular laser beam going through, especially where there's regions of high intensity. The thing is going to go as an intensity squared thing of a scattering. So yes, in that case, have you seen it? Are you experimenting on this?
It's just a thought experiment.
Oh, it's a thought experiment. Okay. Why are you thinking that? What context?
I'm just trying to understand your theory and what are the consequences in different situations that you haven't yet described in this brief talk.
No, it's not the case that the scattering would be any different than really is described by conventional physics. So you need to get to a state where you're producing matter. And I don't know whether you can, you see, the thing is that it will be very dependent on the dwell time because you're kind of slowing light down, you get the Poynting vector nearly zero, but it's quite a hard experiment because to get the things precisely aligned on one another, it's going to be quite hard. So you need a very high Q cavity and some pretty careful experimentation. But I think that if you took a very intense laser beam that was very good quality, then brought it down to a very, very small point, then you'd be potentially creating sub-threshold matter, and that you should maybe scatter off. And that experiment should be tried. So if anyone's got a big high energy laser sitting in the back shed, we want to do some stuff on that, then please feel free. But I think the main contribution to scattering is just going to be box diagram and QED as usual. More questions?
Okay, John, can you explain, or basically the Bell theorem that your model supported, or how would you explain the results of Bell theorem?
I think quantum mechanics is correct, but in a way where relativity is not contradicted. I think people doing the Bell's thing, they always talk about Alice and Bob, and they always talk about something along the lines of, yeah, when Alice changes this, then what Bob sees is this. But you see, the point is that in any photon experiment, the photons are emitted and absorbed at the same point in space-time. That means it always knows what Alice has done. Alice can't do something in the intervening time, because there is no intervening time in the photon rest frame. So I think it's basically all bollocks. I think the entire field is bollocks. Sorry to be so blunt.
Okay, interesting. That's all that I can say. Thank you.
It's at least an opinion, eh?
What are your thoughts on the thing that is waving? Do you think it could be modeled as an elastic solid that has the spatial dimensions, time, and density?
Chantal, I would love to think it could. Yes, I love the background you have there as well. Yes, I think there is an ether. There's a beautiful book by a Polish chap who, at Gdańsk University. I don't know. Do you know him, Jarek? This guy wrote a book on Einstein's. It's a brilliant book. It's not very well known, but there's an emeritus professor at Gdańsk. I've forgotten his name. I'm terribly sorry. I'm getting a bit senile, forgetting things. But he wrote a very good book on this stuff. And he's talking about the ether and about Einstein's modifying view as he went through his life on the ether. And he sort of debunked it at once, as I just did in the whole field. Sorry, I shouldn't do that. But later he took the ether up again. And at one stage he even called it the ether, but he ended up calling it the universal field. But of course, when you look at general relativity as opposed to special relativity, the fact that you have bending of light in that thing means that really you're changing the velocity of light in the medium. You don't observe that because your rulers and clocks also bend with anything you're trying to measure. Yeah. Locally, your speed of light remains constant. But I think bending of space-time is a beautiful way of, and I have a complicated relationship with this because I'm thinking about the space-time bending in 4D and a bit of the space-time being missing. And then that kind of explodes my brain a little bit as to what that actually means in terms of the matrix that one's looking at. So I've thought about this, Martin and I both thought about this really quite a lot in terms of trying to think.
Yeah, Hagen Kleinert, he has shown that the metric tensor, so you can model the whole thing instead of space-time, you can look at it as space density, and you get the same equations, the same, yeah.
I think that's a beautiful, I know.
Velocity of propagation, yes. It's a change of velocity of propagation of electromagnetic wave. There is alternative view for
it is an alternative view. Yes, and or a change in epsilon or mu, change in the refractive index, if you like, of space.
Exactly. Yeah. That.
Yes. So I like all of these, and I like thinking about them, but I don't know if I've come to a solid view to be able to express an opinion. But yes, the fabric of space is being modified by mass. And it is changing it, and it is changing. I think my favorite view is what Jarek said as well, that one really must think about the velocity actually changing, even though you don't observe it to change. So that's a difficult, that really one is looking at a difference in the speed of light. But one can't see that because everything we are, everything we is made of light. So we as light creatures cannot see light changing velocity. That's philosophical.
From one side, from the Fermat principle, we have bending of light. From the other, from slowing down propagation, all the chemistry, biology is based on electromagnetic propagation. So if you slow it down, we get time dilation.
You do, but you don't notice, because if you're in it, you can't see that happening. I think there's a lot of bollocks talked about. Sorry, while I'm on the subject of bollocks and destroying other people's, I think there's a lot of stuff on black holes and so forth that's not particularly satisfactory, because I think people are mixing classical and Einsteinian stuff. I think Viv has a better opinion than I do on that as well. So when Viv talks, it would be better to talk to him about this. He's certainly thought about it more deeply than I have.
So a problem with black hole, I usually emphasize that the question is, are baryons ultimately conserved, the baryon number? So there are a few situations where it is believed that it's variated. One is baryogenesis, creation of more matter than antimatter. Another is Hawking radiation inside the black hole. So taking baryons and finally producing massless radiation. So if baryons can be destroyed, then there are some conditions, some threshold conditions under which they get destroyed, crushed. You can imagine. So
yeah,
where these conditions are happening. So I think that the center of neutron star just before the collapse will exceed any final threshold. Before
I think
it starts
right.
starting.
It's good thinking.
So it should.
I'm with you on that.
It should start burning baryons before start collapse to black hole. But that's
I think maybe. I mean, my own view is there's no such thing as a black hole, really, because I think that as you're changing the scale of space and time, all that happens is the scale of space and time changes, so that locally you don't observe any difference. And if you think about the universe we live in, that's also the same conditions as for a black hole, where we're at the center of that black hole, and the edge of it is the edge of the universe. You know, light can't escape from the universe in which we live either. It's just a black hole condition as well. So I think that because the space is being bent as you move into these things, you don't notice anything, you don't have some barrier as you need in Hawking radiation. I think that's also, I don't think that really stands proper scrutiny if you do the whole theory in general relativity, at least for what I've seen of it. I'm no expert, so I wouldn't like to express too strong an opinion there.
If you get Viv to do a talk on this, he has a great view about his whole concept of gravity, and he goes into not only redshift, but he goes into black holes and neutron stars and how it all fits together according to his view, and it's quite compelling.
I think it's beautiful, Viv's view. He expands general relativity to take some extra terms in the expansion that Einstein also talked about. And Einstein took only the first term. Viv takes an exponential there, and it looks much nicer to me. So I would persuade him to talk. I think he doesn't want to talk about that first. I think he's going to talk about his electron model, which I think he'd be better off talking about the cosmological stuff there. It's very beautiful. Anyway, Viv's not with us at the moment because he's in the east coast of Australia and it's the middle of the night for him. So he's going to look at the recording. I'm just having a look at some of these comments. If the two photon energies don't sum to 511 MeV, so the belt doesn't quite bite its tail, will they still interact and scatter off each other in different directions? Yes, but also electrodynamically that happens. If you get close to threshold, they scatter more. That was Mark himself. Oh, that was Mark. Oh yeah, I know Mark. Yes, good old Mark. Right, let me just see. Are there any other questions that people had on the way? Yeah, you're quite right, Jarek, about Demelt's argument. Sorry, I'm just having a quick look through some of these things. Yes, the galactic charges connect. Yeah, okay, cool. Yeah, good. I'll look at those comments when we're finished as well. The fat photons are fun. People have observed these things coming in as sort of H bar, 4H bar, 9H bar, etc. Cool stuff. So where the electrons are actually interfering with themselves, well, where two photons are interfering with themselves, with each other. Yeah, with themselves and each other.
Do you think that radio waves are not quantized?
That's a very good
question. Cosmic microwave background radiation, is it quantized? That's the big question.
I think that it kind of fits in with the with the question that was asked earlier as well. I think that theory allows for non-quantized radiation. The quantization comes from the emitter and the absorber.
Exactly, that's what I was thinking. Yeah, because radio waves, you can generate any kind of wave, really, right?
Yeah,
there's nothing quantum mechanical.
Yeah, I think maybe not. I think that when we're talking about quantized, I think that quantization becomes sharper as the emitter becomes smaller, and I think that one can possibly create stuff that's non-quantized at the low energy end.
Yes, so there are. So example of such effect is this spontaneous down conversion, SPDC crystal, that you take one photon and produces two photons from them. So that's clearly validate the number of photons.
Yeah, that's right. Yes. No, that's a very good question, and to which I don't have a very solid answer, I'm afraid. So,
yes, I also agree that it's due to the creation in atoms and absorption also usually in atoms, which have quantization of orbitals from some resonance condition.
I've got a radio. Let's put it this way: light waves or photons are not radio waves. I've actually made a study of not a quantized radio wave, but an elementary radio wave, which is interesting. And basically, we need to look at, we can't look at photons as radio waves as described by the Maxwell equations, out of the simple fact that if we have an electron transition, which we know that physics tells us is instantaneous, and then I should have, how can that be of a specific frequency if it's not, if it's instantaneous? So we must actually look at the photon as a particle of zero size, which has possibly has a de Broglie wave attached to it, which is a frequency then that we observe.
Yeah, that sounds right. That sounds right. I mean, when you're creating radio, that's so big, you have lots of time to do stuff to that phase front, and you can chirp something. You can have a lot of different frequencies which are related to that. And I think you're on the right lines there, thinking those things. Is that based on any experiment, though, Anton?
No, it's just, well, basically, if you look at my papers, and I've had some talks, and for the next talk, I'll make sure that you all are invited. And I will introduce myself on the particle group tomorrow or so, just who I am, so that you all know who I am. But I've got a completely different view of things. I actually attended a conference in Edinburgh this week called New Directions in Physics, organized by Neil Turok. And I actually managed to show my work to him. He gave me about 10 to 15 minutes, which is a lot for him to spend time with me at the conference that he's organizing. And basically, at the end, as we were going out together to lunch, he said, even if you are right, you can't be right because of Bell's inequality. And that is exactly the same question that I posed to you. And basically, I can handle it, fortunately, So, he's put me onto new ideas, which I'm working on right now.
Good.
Yes, so the Bell cannot be just ignored. Like John has tried. There are some correlations which are not easy to explain. And very nice example is that it's called Mermin's inequality. That tossing 3 coins, at least two give the same. So it's completely obvious, but it can be violated in quantum mechanics. This is probability of that A equal B plus of A equals C plus B equals C is greater or equal than 1. But for quantum, we can go 0.6, 0.7, 0.8, I think. So it's not something like you could ignore. But can we do it with the classical field theories we are thinking about? I think we can. And my answer is that instead of solving it with Euler-Lagrange equation, we should solve it with the least action principle, this time symmetric view. In this way, you get the Born rule. I said so there is this given moment due to time symmetry is in the intersection between past, and there are two amplitudes going from one for past, the second from the future, and we need to multiply them. And it is in many situations. For example, in this scattering matrix, you get two amplitudes, one from the past, second from the future. So we need time symmetric formulas to get the Born rule, which can lead to Bell variation, and we can get it, for example, by solving classical field theories not with the Euler-Lagrange, but with the least action principle. We can translate such solutions between, but if originally solved with one of them, they have very different properties.
Okay, that sounds interesting too. Have you given talks on this or papers on this, Jarek?
Yes. So one is maximal entropy random walk. So this is random walk with which I have started my adventure with this controversial part of physics, let's say, in 2006, I think, 2008-9. So this is random walk chosen according to the maximal entropy principle. So it turns out a bit different than the standard diffusion, and from physical perspective, better motivated. And turns out it had the same formulas for stationary probability distribution as the quantum mechanics. It has much stronger localization properties. You get the Anderson-like localization with this random walk. You have the derivation, and the derivation is based on this. It's, for example, random walk along Ising model. If you do it right, assuming Boltzmann ensemble of paths, then you get these squares, you get the Born rules. That the probability of some configuration given position is product of two amplitudes going from left and right from the symmetry, it's spatial symmetry. So I have a paper I will send you also.
Okay, that's good. Good. Right, so I hope I've convinced you all that this new theory is worth thinking about and that it has some content to it. Are there any problems any of you had with the answers that I've given? Anything where people thought, no, that can't be right because? It's all of course within the context that the theory might be correct, which of course it may not be. So within the context of the theory, I think that's always the case.
If I properly understood, you are working in momentum space usually, or also the
working in what? Sorry, Jarek, you're cracking.
Momentum space, or you've mentioned that you work in momentum space, but what in the position space?
Well, working in all the different spaces, and in fact, Arnie and I are busy having a look at how those spaces fit together in more complicated systems, such as atoms and molecules and the solid state. So we're looking at extending because some of the spaces have extent. Obviously, the electric field space has inverse square extent, but others have a sufficient extent that they do act on adjacent molecules quite strongly. So while the electric field is the only game in town for sort of several atoms distance, for interatomic distances and molecules and crystals as well, the interactions between adjacent atoms are also pretty strong in spin space and magnetic space as well as electric space. Well, magnetic space, obviously, we know about already, but the spin space one is a kind of a new thing to look at. So we're looking at those interactions as well. So we're working in all of the different spaces, the answer to your question. The thing is, the thing's only toroidal in momentum space. And that's not the space you observe if you just look at the thing by banging rocks together. Of course, you observe real space, position space.
So charge quantization can be seen as being in Gauss law in position spaces. So we need to make that the Gauss law can only return integer charges. So that's for me the question for charge quantization. Can you explain it?
Yes.
So
So, I mean,
why
what-
did Gauss law?
Well, just using Gauss's law to get the charge from the field. So you know the length scale over which the thing is vibrating. So that vibration translates also over to a spherical vibration of that size in normal space. So the characteristic length scale here is lambda c over 4 pi. So what you do to get the charge in the electron is you say, okay, well, let's assume all the charge originates at lambda c over 4 pi. So it all appears as the double loop is just stuff. It's just so it's just the whole thing on top of one another. So let's do that. Let's calculate that extremal possibility for the electric charge, and there we get 0.91 e. And then let's calculate the other extremal charge, which is where the whole thing is maximally extended, and that's about, I think, about 15 e. So what you say is so what that says, it says, okay, that means the thing is not quite lambda c over 4 pi, but it's lambda c over 4 pi plus a bit on average. And plus the bit is about 10% or 5%, I think. Yes.
So you are saying that electric charge is blurred in your view.
Is what? It's blued?
Blurred. Yes. So it's
Blurred.
not exactly
Blurred,
but
fuzzy.
Blurred.
Fuzzy, yes.
Blurred. Yeah. Yes. It's a difficult word. Yes. It's not that it's blurred. It's that it sits in a mode structure. So it can't all sit. It's not physical to have the whole thing sitting on top of itself. So the thing has some distribution. That distribution would both go to smaller distances, which will contribute less, and it will go to larger distances, which will contribute more. But the larger distances contribute because what one needs to do is one needs to draw the boundary further out where the electric field is. That increases the apparent charge. So
the problem is, can you with your change of configuration of your belt change the charge inside?
Yes. As you increase,
that's against the Gauss law. Gauss law says that you have an area and you cannot change charge. You can only create pairs, quasi-charges.
Oh no!
And you can.
Oh yes, of course it is. The thing is that you can't change that size inside. That size is determined by the dynamics of whatever it is. So it's not. You don't have a knob to change the size. Where this is a purely calculational thing. So if you calculate it all at the eye of the torus, then you get 0.91 e. If you calculate it all at the edge of the boundary at lambda c over 2 pi, then you get about 15 e, which is clearly non-physical. I mean, it would be a completely empty electron with nothing in it at all. So, but all it's saying is the true answer lies somewhere in between, and probably closer to the 0.91 e. But it's not something which one changes by squashing the electron or whatever. It's not squashable at that kind of level. But so it's only theoretically you only have a theoretical knob, not an actual knob on the electron. The electron will equilibrate.
And now for Coulomb interaction, you would need to get the Coulomb potential. That having two electrons or electron positron in various distances, the energy changes with 1 over distance. Can you
That's right.
derive it or?
Yes, you can. And in fact, Arnie and I have been working on positronium, ortho and para positronium, and having a look at the differences between them. But yes, you can. Yes, and it's an interesting study.
Yes, and so there is this nice effect, the running coupling here, and Matthew has written in the paper that you get the agreement that for very very small distances you get a change, a small change in the Coulomb interaction.
Increasing the charge. Yes, you're right. Yeah, no, the running coupling constant stuff is something which we had to. I mean, it's a well-known effect in quantum electrodynamics. You know that. It's in the big text quantum electrodynamics textbooks, the running coupling. I've got one here actually, but yeah, the coupling constant does run, and I think, but it's an agreement with QED though, the running of the coupling constant, as far as I know,
Yes.
as far as I remember.
Yes, but we need to show it that it is kind of a finite size structure of electron. But for very small distances, that there is some additions. Yeah.
Yes, when you squash it down, then the coupling gets a bit higher. I think it's because you start overlapping. into the electron understructure. So you get a repulsion which, well, okay, speculation. I won't speculate too much. I've speculated enough already. So.
Yes. So another there is this problem that with infinities you want to cut hole in space-time, and if I properly understood, that in the position space you want to integrate from some radius.
No, you don't need to cut anything off because you can do the whole integral. You can integrate the whole space. So it's not a cutoff. It's the cutoffs. It's not a cutoff that you impose. It's a cutoff which is natural. So
it is cutting a hole in space-time. What you are doing? No.
Well, yeah, you're looking at field rather than charge. So yes, it's nowhere in.
So the question is, what is the field down to the radius 0? So another question is that
I'll ask the question. There is no radius 0. There's nothing at radius 0. It's a hole. Yes, you're right. It's a hole.
Yeah. So you are cutting hole in space-time. I really don't like this.
That's right. There's a hole in space-time. It's 0 to infinity and it's 0 at 0. So it comes to
a physical question related to this running coupling curve question is that having electron, and what is the mean energy density in distance r from electron? So for a large distance, you have 1 over r to power 4. The question is what's happening when you go down to 0?
Okay, that's a very good question. And I think when you go to 0, it's 0. The potential is 0 because you've got the same field on all sides. You have cancellation of field in the center. So when you get to 0, it's 0. I suppose when you get to the I haven't really looked at that because what you do is you look from the outside of it as though it's a spherical charge to get. I think if you started bringing the boundary in, then what you'd find that you were losing, that the charge would go down. You want to put a boundary around the whole thing and look at it from the outside.
Yes, so that's the question about the running coupling, but surprisingly, it does not go down, but goes up. The interaction is stronger. Running coupling.
It does go up. It goes up in QED as well.
Does cutting hole is not enough to hear.
I think in QED you have this idea that you have the in quantum dynamics, of course, you have a 0 size electron, so you have the infinity. So the idea is that you have a negative infinite charge at the origin, and that comes up and that produces a huge peak vacuum polarization, and then it comes down and then it rolls off in such a way that the integral charge is exactly Q, which does sound a little bit far-fetched, but that's how QED does its renormalization. I think that's a bit of a cheat, that method. But as I understand, it's a long time since. I'm trying to remember exactly by the running I think the running coupling constant increased in QED, but I've forgotten why and how. I'll look it up again. I'll remind myself how the thing works in QED. It's been a long time since I've played with QED, around 40 years. So, but I still have the book.
This is very related to this problem. I don't think we have to cut a hole. We cannot do it. There is some field down to 0. The question is, what is this field? And it can be repaired. There are ways like Manfred is doing or me, that we have Higgs potential. We have a field of unitary vectors outside that it performs a Hedgehog, a topological charge for charge quantization, that the Gauss law counts topological charge. We can do it, but Gauss brought here. And what's happening in the center? We say that there is Higgs potential. So Higgs potential prefers unitary vectors, but can get down to 0 vector. So in the center goes down to 0 vector, but it costs energy. It costs this Higgs energy. So it prevents. So usually the field wants to be unitary, but to prevent this infinity in the center of charge, it can go down to 0, but at cost of Higgs potential. So kind of electromagnetics makes no sense in the center of charge. So it deforms into other interactions in the Higgs potential in the center of particle.
Yeah, people do various things to get away from this, but as I say, I don't really need to do them in this model because there are no infinities. Everything's finite, and
yeah. So
it goes down to yeah. No,
so
there's still mysteries.
Not an answer, and you can do it better. Yes.
Well, I don't know if I can do it better or not, but my theory is my theory, and it works as well as it works. And everything's down to experiment eventually. Does it agree or not with experiment? So far,
the only experiment I know is the running coupling, and Manfred-Faber calculation agrees with running coupling, and it can be seen as this regularization of this infinite energy of electric field down to 511 keV at most, the mass of electron. To do it, so integrating from 1,4 Fermi to infinity, you get 511 keV from energy of electric field alone. So you need deformation not in 10 to minus 18 meters, but in 10 to minus 15 meters.
You need to do better than 10 to the minus 15, 10 to the minus 13 as well. Absolutely. The classical radius of electrons, what is it, 2.4 10 to the minus 15 meters or so, isn't it? So it can't be smaller than that. No, it's not physical. I like what man
from one side, electric field goes to infinity, 1 over m to power square. But we need some deformation because of the infinity of energy of electric field. So doing this deformation, it needs deformation in a few femtometer distance. It's very large, but it's just deformation not to exceed 511 keV with electric field alone. And
my integral takes place at outside lambda c over 2, so it's 10 to the minus. It's only going down to 10 to the minus 13 meters, and the only bit that's left. Well, actually, I didn't really talk about it, but the point is that there's still electric field outside lambda c over 2, but that's the bit that's not rotating. That's the bit that's responsible for the g minus 2, and it works exactly in quantum electrodynamics, but also in my theory, it also works exactly. So, but that length scale, so you don't integrate down to 0, you only integrate down to, or between, well, you get all of the field from lambda c over 4 pi to lambda c over 2. And anything outside of that's non-rotational, so it's not part of the localized photon. And that fraction is about 1,000th of the total mass of the electron then at that size. So it's not a very large fraction, but it is responsible for g minus 2. Anyway, I want to talk to Manfred more about, that was a very brief talk, but very, very interesting. So I want to talk more about that at this stage. Yeah, I love what you two are doing. I want to join in. It's good. It looks like good fun.
Yeah, so there are many similarities, but so I think that the main difference is here that we don't cut holes in space-time, but we regularize the field down to 0.
You both know a lot more about my theory now than I know about yours, given that I've talked to you for 3 hours about it, and you've talked about 15 minutes. So.
We can talk again in detail, so no problem.
Yeah, you're right. Anyway, guys, I'm beginning to fade a little bit. I'd like to take a short break anyway. So, and I've managed to spill some stuff.
Thank you very much.
I think I'll take
for your laptop.
Thank you for listening and for paying attention for so long. I'll look forward.
Next time.
Thanks, John. That was great.
Pleasure, everybody. It's a pleasure to see you all.
Have a nice evening, and see you next time.
Great.
Take care, thanks.
Good night, everyone.